test. Thank you. I think I managed with the screen. Okay. Yeah, something is not right. Yeah? One of them. This one. But I think it looks exactly the same. Yeah. Okay, let me try to move it. Yeah. Okay, so let me explain what we are doing with this model. So I stopped at this point, promising to discuss how the parameters of the model are fixed. Before I discuss how the parameters are fixed, so I should probably say that so we have to take care about the structure functions here, so the model of the structure functions which is used here for the proton and neutron is basically based on the Alekhin PDFs with his extraction of higher twists, and also the target mass corrections. So target mass corrections a kind of important correction if Q square is not large, and also at large x it's important to take it into account. So the spectral function I have already discussed. There are nuclear pine corrections. So for that we have the set of equations which follow from equation of motion for nucleon and pine fields. So we try to avoid a direct calculation of Pi correction, but rather try to constrain it using the light cone momentum sum rule and also the equation of motion for the fields. So here we can parameterizing the Pi distribution function, one can constrain its parameters using these equations. So the advantage of this that the light cone balance equation is fulfilled automatically in this approach, so you don't have to worry about that. And so the coherent part of interaction, this one, which is important on small x, is governed by the effective amplitude, and this effective amplitude, for this particular analysis, we have only one amplitude in the transverse channel. In principle, we need also the longitudinal amplitude, but for that we have a model how to calculate it. So the idea was to confront this model with data and try to extract the off-shell correction and the parameters of the amplitude. So the off-shell correction is a kind of a structure function of the nucleon structure function. So that if we parameterize it, then these parameters are universal for all nuclei. So that, and in fact, it was possible. In fact, this is the model which was tried in this analysis. So in fact, it was possible to parameterize this correction in terms of 3 parameters. Well, here are 4 parameters, but after initial trials, so we found that this parameter is strongly correlated with one of the zeros here, and so it was fixed eventually. So it's 3 parameters of the structure of the shell correction. We assumed it's independent of q square, and also so we have to take care of the effective amplitude. For that we have we would like to have the limit of q square 0 fixed in this approach because at this limit, so we know something from the vector meson dominance model, and that was actually the tool which we used to constrain the effective cross section at low q square. And in order to interpolate between the low q square region and large q square region, so we just used a simple monopole formula, and it turns out that in the fits to the nuclear ratios, we are always preferring the parameter sigma 1 about 0. So it was eventually also fixed in this analysis. So in total, yeah, I have to say about the real part of the amplitude. So the real part of the amplitude also was fixed, equal to minus 0.0, again, for the reason to have a correspondence with vector meson dominance model at low q square. So we assume no q square dependence here. So then we have here only one parameter in this particular model, that the transition scale, which we tried to fix from data. So data had the sensitivity to that at small region. So this is actually a summary of the results. So the final chi-square was pretty good for this analysis. So the probability of the fit is pretty high for 4-parameter fit. So we have tried to do the fits for different subsets of the ratios, selecting selecting the ratios for light nuclei, intermediate nuclei, heavy nuclei, and the full set of the ratios. So in all these fits, the parameters were consistent. So I probably don't have time to talk about all the details. So please refer to the paper where this procedure is described. So let me just summarize the results. So this is how the ratios look like. Here I present the ratio for the lightest nuclei which was used in the analysis, helium-4. So the data comes from basically from two experiments, NMC and E139. And so we found a very good agreement over all kinematical regions, but not only for helium-4, also for all sets of nuclei it works. So this is how the correction looks for heavy nuclei. Gold and lead combined in these two panels, focusing at large X and low X. This is the shape of the off-shell function extracted from this analysis. So it changes sign 2 times, so that at intermediate X about 0.4. So the positive sign of this function means that the off-shell correction is negative because it is multiplied by the nucleon virtuality in actual correction, which is negative. So then in this region, so the data prefers to have positive correction. And this is the shape of the cross-section, effective cross-section. So the parameter was the transition scale was about 1 GeV square, and this cross-section is constrained by data in this region, since this is basically no data about shadowing exist for higher Q square. So the strongest constraint comes from the NMC data at low X. So I probably don't have time to discuss it. This is actually this blue curve is an attempt to calculate the asymptotic cross section. So this is effective cross section which comes from the feed. So one can trust to this cross section for Q square less than 20. But this cross section was calculated from the normalization condition. Actually, the requirement that the contribution, the requirement of cancellation of various corrections to the valence quark distribution, to the normalization of the valence quark distribution, can be treated as an equation on the cross section. So one can extract this cross section, and this is shown by blue in this plot. Here is an idea of the magnitude and the shape of the nuclear corrections coming from different effects. So this FMB means Fermi motion and binding. So basically the correction from the spectral function, from the Smerin with the spectral function. Then the major correction comes after we include the off-shell correction. This is denoted as OS, or shell. And then in the small X region, so we have the competition between the pine correction and nuclear shedding correction. So this is drawn for gold at q squared 10. So the important test, so there was the calculation with the deuteron. So the deuteron always sitting in the denominator of the ratios which were analyzed, but and it's fully determined in terms of the wave. The correction to the deuteron is determined by the wave function, and the correction of at large x, I should say that large x, it's fully determined by the wave function. At small x, so we have a couple of corrections which are not reduced to the wave function. These are pine correction, coherent correction, which are given in terms of effective amplitudes. But this data were not used in the analysis, so that was used as a test of the reliability of this model. So that was, and we found that the calculation of the deuterium of the proton ratio and comparison with E665 data shows a very nice agreement of the result with this data. And the right panel is comparison of the isoscalar ratio, deuterium over isoscalar nucleon. So this ratio is not measured directly, as we know, and those points are extractions from E169 analysis with nuclear density model, and it turns out that our calculation were pretty close to this extraction in this region for x not too large. So that at larger x the agreement is not as good, but there is a reason for that. So in density model, in nuclear density model, the corrections due to momentum distribution are not accounted. This is how the q-square dependence looks like. Here I show the ratio of tin over carbon, NMC data for different x bins as a function of q-square, and the qualitative picture is actually drawn from the right. So here the ratio of iron over the nucleon is drawn for a few different q-square, from which one can figure out that the region of intermediate x is not affected by q-square dependent effects, nuclear effects. So the q-square dependence comes from the edge, from the small x and large x region. Because of different physics effect, in fact. So this, the small x is governed by effective, by coherent effects, and the q-square dependence goes from the effective cross-section. But the large x is, this q-square dependence is mainly due to target mass corrections. So let me show the comparison with recent JLab data. So it's not a fit, it's a calculation. So calculation for the JLab kinematics in two different approximations. So here are three different nuclei: carbon, beryllium, and helium-4. And the blue curve is what we get if we remove the short range correlation part from the spectral function. So then and the black one is the full calculation. So here we have sensitivity, and it's clear that without the high momentum and high excitation energy part, it would be difficult to reproduce data here. Okay.
So is this the one of the bases for the Jefferson Lab, assuming that the EMC effect and short-range correlations are connected? I remember there was a paper recently.
Oh, okay. This is a little bit different story, but this is one of the motivations for that too. So without high momentum and high energy part in the spectral function, it would be impossible to reproduce not only GLAB data but also the other data. Here is the comparison with Hermes data focused at low X. Also in comparison with NMC ratio. So these pink triangles are the ratio for Hermes, which is nitrogen over deuterium, and NMC has a little bit different target, carbon 12 over deuterium. The A dependence here is marginal, and the major difference which comes between these two measurements and the curve is Q square dependence. The two experiments have different kinematical conditions, so the Q square of Hermes is systematically smaller than NMC. Okay, so if when we talk about light nuclei, then so we discussed a lot in the previous sessions about consistency of different models. But there also the question of consistency of different data. So then, how we could tell that the data from different experiments are consistent or not? So the question we are asking here is. Suppose we have the measurement. So the GLAB gives the measurement of this, provides the measurement of this ratio, helium-3 over deuterium, non-other scalar ratio. From previous measurements from NMC, we know pretty good the ratio D over P. So D over P is also known from E665 experiment. So then the question is, do we have any handle to check if these measurements are compatible and consistent with each other? So the first answer, probably not, because the targets are different. But if we think of just a little bit, then we could try to compare the N over P ratio extracted from these two measurements, and that would be the tool how we can possibly judge about the consistency of different data. So so let me be a little bit fast. So here is actually the example of an attempt of such a comparison. So we extracted the N over P, F to N over F to P ratio from the measured ratio of the nuclear structure functions from two ratios. So D over P, which is shown by green, and helium-3 over deuterium. So if you assume non-nuclear effects, and it's very easy actually, and this is and this extraction is shown by open symbols, open circles for helium-3 and open squares for deuterium. So if there is some uncertainty about the inclusion of nuclear effects, but what we know experimentally, that in the region between 0.3 and 0.4, the nuclear effects cancel for most of the targets which are known, actually for all the targets. And we also have a calculation of nuclear effects for both targets which are shown here. They also confirm that the nuclear effects cancel in the region between 0.3 and 0.4. So we may use this observation to compare N/P ratios extracted from different experiments. And we found that actually those ratios are quite different. So there is about 15% difference between the ratios coming from JLab experiment at the red points and the ratios extracted from NMC experiment. And actually, so if we try to rescale the N/P ratio for JLab experiment, so it's possible to reconcile two different measurements for this helium-3 or deuterium ratio, which were early done by Hermes experiment and recently by JLab experiment. These two measurements have an overlap exactly in this region between 0.3 and 0.4. And if we blindly compare this ratio, then there is a clear mismatch and about 3% difference between this data. But if we try to correct for isoscalarity effect, the JLab data, which has corrected N/P.
About 3 or 4 more minutes.
Okay. I'm rounding up. So this is an attempt to study the consistency of data. So that's the observation is just let me make a statement. So that those two data sets from Hermes and JLab can be reconciled if you take care of N/P ratio and try to renormalize this ratio in JLab experiment. So let me briefly stop at the Drell-Yan calculation, which is kind of important for this model. So we know that in the Drell-Yan reaction, so we in this particular kinematical region, so we are sensitive to the antiquarks, to the ratio of antiquarks in the target. And there was a dedicated experiment to measure this ratio E772 with the result that there is no enhancement of antiquark distributions over in heavy targets, which were expected on the ground of the Pine correction model. So let me as a final remark. So let me. So we have done calculation of these ratios. So there are a few different contributions to antiquarks in the target. So the corrections which are coming from the spectral smearing averaging with the spectral function, Pine correction, and also the shading correction. So the shading correction for the anti-quark distribution is calculated in this approach in terms of the shading corrections for the parton distributions with definite C parity. So for C even, which would correspond to F2, and C odd, which corresponds to valence quark distribution or F3 structure function. So the interesting observation that there is an enhancement factor for the shading correction staying here in front of the difference of these two contributions, R plus and R minus. Why enhancement? Because it's quite a big factor at large x of x about 0.1, because it's a ratio of valence quark distribution over the anti-quark distribution, and this factor effectively enhances the shading correction for anti-quarks. So the net result that there is a quite strong cancellation between different contributions in this region, and the Pine correction almost exactly is cancelled by the shading correction. And this is how the results look like for the actual Drell-Yan yields of E772 experiment, calculated without and with energy quark energy loss. So it's a quite good agreement with the data. And so this is the final slide. I will probably stop here. This is the more detailed comparison of these ratios, split it in terms of the Q-square bins. So the bins for the mass of die quark in the final state. So you may see that there is quite a good agreement here. So let me just summarize. So thank you for attention. So that let me just summarize. So we developed a semi-microscopic model for deep inelastic scattering, for nuclear deep inelastic scattering that includes a few major nuclear corrections. Some of these corrections we calculate. Some of the other corrections are fixed from data. So the comparison of this model with recent data shows good performance of this model. So in particular, so JLab data can be reproduced by calculation using our model, and also there is interesting cancellation between the Pine correction and shading correction for anti-quark distribution, which shows up in the Drell-Yan reaction. So thank you very much.
Thank you. All right, I've decided that my presentation will be the open mic session on Friday, so we can actually go immediately to the review of week number 1.